right, so this week we're going to take a look at graphing sine and cosine to start. As I said on Wednesday or Thursday, we'll get to look at some of the other trig functions like tangent, cotangent, secant, and cosecant. But these two graphs are nice to start out with because they look very similar. And they're a little easier to deal with than some of the other trig functions. All right, first, these kind of graphs are called periodic functions. Okay? All the trig functions, sine, cosine, tangent, all of them. They're all called periodic functions. Okay? Because what happens is you get this behavior that the graph repeats itself. Okay? All the y values will repeat itself over a certain set of x values. Right? And I'll show you a picture to kind of explain what we mean by that. Okay, but all the y values of the graph continually repeat themselves over a certain interval, okay, or a certain set of x values. All right, so let's take a look at the graph of sine. Okay, most of what we do this week is going to be in radians. You can do it in degrees, but we'll probably stick with radians for most things. Generally, if I want to graph a trig function really quick, there's a different zoom we haven't used before. Okay, we talked about zoom 7 in here. No, zoom 7 basically sets your window up for graphing a trig function. All right, so anytime you're not sure, that's a good starting point. Zoom 7. Okay, and there's our graph of sine. All right, so let's kind of see how that ties into the definition. It says the y values repeat themselves over a given set of x values. Right, so let me just trace this part right here. Okay, that part that I just traced in red, I just want to move it down. What I did is I traced every possible y value you're going to get. You starting at 0, you go up to the highest point, which is 1, back down to 0, keep going to the lowest point, which is -1, and then back to 0. After that, it's just going to repeat itself. Okay? So here, if you just copy and paste it, you get another section of it, or copy and paste it the other way, and you get another section. All right? So does everybody see you're never going to get any y values other than between 1 and -1 forever? That never changes here. All right, and that interval, okay, basically that distance from here to here, okay, that's called the period of the function. Okay, it's basically how many degrees or how many radians you have to go through before you get back to the starting point, and the graph is going to repeat itself again. Does anybody have a guess how long that is for sine and cosine? How many radians or how many degrees you have to go through before you get all the way back to the beginning?
11.
How many?
11.
How'd you get that?
I don't know, I just went onto the table, and the first time I got the numbers was at 11.
By 11? All right, no, not 11, but it's actually a nice number we've worked with before. Think of like your unit circle. How many degrees do you have to go through before you get back to where you started? Yeah, 360 degrees. All right. So this would represent 0. And if we're doing it in radians, that would be 2 pi. All right. So 2 pi radians, or 360 degrees, is what you have to go through to get all the way through one period of the function. And generally, when we sketch sine and cosine, all I'm going to have you guys do is sketch one period. What I have in red right here is one period of the function. Okay, we know that it goes on forever, left and right, but we're just going to be sketching a small section. Okay, another name for a period is called a cycle. Okay, that's one cycle of the graph of sine. Cycle is used more in some other trades. Anybody in electrical? Electrical? Do you ever use this unit, cycles per second? Or do you know, do you remember what you call that? Does anybody know what they call that? Cycles per second? Something you can measure in a outlet on the wall. It's not the voltage. But what else can you measure? Not amperage. That would have to do with the maybe the thickness of the wire and the circuit breaker it's on. But there's something else you can measure, and it's different like in the US than it is in like European countries. And voltage is one thing that's different, but this is something else.
The velocity?
The what?
The velocity?
No. Velocity. It's abbreviated with 2 letters.
Alternating current.
No, not alternating current. Good. Got good guesses.
5.6 kilohertz.
Anybody know? Have you seen that before? Hertz.
Yeah, with a 0 under it.
Okay, so hertz is a measure of how many cycles per second. In the case of alternating current, it's how many times the current is alternating per second. Okay, so 60 is the normal number that we have in the US, 60 hertz. With a sound frequency, we also can talk about hertz, but it doesn't have to do really with like an electrical wave. It has more to do with the pitch we would hear a sound at. Right? So it would be higher pitch or lower pitch if you change the hertz. Right, so again, you can use the word cycle, one cycle, but I'll probably use the word period. Okay, one period of sine or cosine. I didn't show you guys cosine, but let's just look at that compared to sine. Anybody describe the difference there between sine and cosine? Or, no, I think it's the same width. Like, what could you do to sine, or what could you do to cosine to change it? Like, how would you move it?
It was shifted either to the left or to the right.
Yeah, depending on which one you're looking at. If you take the red one and shift it right, or take the blue one and shift it left, they would be the same. So sine and cosine are just a horizontal shift of each other. Okay, so they're very similar. All right. Great, so generally when we want to graph sine and cosine, okay, we need to pick 5 points. Okay, the 5 points that we generally like to find are where it starts, where it stops, okay, for one period, the highest value, the lowest value, and then a value right in the middle. Right? If we can get those 5 points, it'll give us a nice curve. Okay, and if you look at them, they're all equally spaced. They're all pi over 2 radians apart. Does anybody remember what that would be in degrees? Yeah.
360?
60 would be pi over 3. Pi over 3. 180 is pi. So we're getting closer. Pi over 2 would be 90. Okay. These are all 90 degrees apart. 0, 90, 180, 270, 360. And then after that, the graph is going to start over and repeat that wave. Okay. So this is one period of sine. All right, so anytime we want to graph sine or cosine, first thing we have to figure out is where it starts. And then we can figure out where it's going to go to. All right, so these 2 tables I'm about to give you, okay, one for sine, one for cosine, they're very important. We're going to use them every time we graph sine and cosine this week. All right, and let's just kind of look at our x values. Okay, don't worry about cosine. We'll come back to that one in a second. And let's see if we can figure out our y values. So when x is at 0, I'm going to look at my graph of sine. Y is also at 0. Okay, so that's 1 point on sine. 0, 0. Okay, how about pi over 2. When x is pi over 2, what's my y value?
1.
Yep, I'm up at 1. Okay, and then when x is pi, we're back at 0. 3 pi over 2, negative 1. And then 2 pi,
0.
yep, back to 0. Right, so those are our starting points for sine. Right, so anytime we're going to do a transformation of sine, we'll start with these. And that's going to help us to figure out our transformation. All right, now cosine has the same x values. Let's look at the graph and see if we can figure out the y values. Okay, so when x is 0, what's cosine at? No, this one's not at 0, 0. 1. Okay, when x is 0, y is at 1. Okay, how about at pi over 2? Yep, we're at 0. And then pi, we're at negative 1. And then 3 pi over 2. So 3 pi over 2, that's my third mark. 0. And then 2 pi, I'm back at 1. Okay? So those are my 5 starting points for cosine. Okay, any question on those original tables? Okay. Biggest mistake I usually see, we're going to do problems that have sine, then we'll do some other problems that have cosine. Just make sure you use the right table. If it's a sine problem, use the one on the left. Cosine, use the one on the right. Okay, does everybody have the 2 tables?
No.
All right. So up until Wednesday, okay, all we're going to do is one transformation at a time. Okay, we're going to either shift it left or we could shift it right, and that's it. Okay, or we could shift it up, we could shift down, okay, or we could stretch it left and right, or we could stretch up and down. Okay. Since we're only going to do one transformation at a time, one of these columns is going to stay the same, and then one of them will change. For example, if I were to shift up, what values would that affect? X's or Y's? Yeah, it would only affect the Y's. Okay? You wouldn't change the X's if you're just going to shift up, and that's all you're going to do. Okay? Likewise, if I was going to shift to the left or to the right, which values would that affect? That's your X's. All right? So if you're going to shift left and right, you're not going to mess with the Y's. Okay? On Wednesday, we'll talk about maybe shifting something up and right or down and left or something like that. Okay, 2 things in the same problem. Okay, but not today or tomorrow. All right, so all that information I just gave you was basically all background information about sine and cosine. Okay, now I'm going to specifically talk about a phase shift. Okay, you've seen this kind of transformation before. We've never called it a phase shift. We usually call it a horizontal shift. But a phase shift is just when you move left or right. Okay, and you guys have already seen a phase shift today. I think it was Cheryl or somebody mentioned sine and cosine. Basically, if you just take one and move it left or move it right, you get the other. Well, that's exactly what sine and cosine are. They are phase shifts of each other. And the other thing that's nice about sine and cosine, all the transformations are exactly the same as everything you already know. Okay? So a phase shift is when we add or subtract inside the parentheses. Okay? It's inside the argument to the trig function. Right? If we were doing another function, this would be similar to like square root of x plus 2. That's a horizontal shift of square root, adding or subtracting under the root. Okay, but we got to be careful. If you add, which way do you think that's going to move your graph? Left or right? Left. Okay. Add is going to move left, and minus is going to move right. It's the same rule we've had all year. Everything that has to do with moving or changing the graph horizontally is the opposite of what you would think. Okay. When we get into vertical, vertical is exactly what you would think. Plus is up, minus is down. Okay, we'll look at that one at the end of today. Right, but this is our phase shift. Right, so if you do minus a value, it shifts right. If you do plus a value, it shifts left. Now, technically, when we do a phase shift, you can shift by anything you want. Okay. Some amounts to shift by are more common than others. For example, shifting by 45 degrees, 90 degrees, and 180 degrees. Those are the most common ones we do. But, I mean, if you really wanted, you could technically shift something by 30.96 degrees. Or 36.72. You can shift by anything you want. Okay, but I'll just show you the common ones again. So 45, or pi over 2, 90, or well, I can't quite get 90, but that's about 90. And then 180 would be about right there. Okay, 180 is, they're almost opposite each other now. Right, so we'll talk about what this would sound like if we played it in a little bit. Okay, so any question on the phase shift, which way it moves? All right, so with a phase shift, if we're going to move things left and right, which one of these columns isn't affected at all?
Y.
Yeah, the y's. Okay, so for phase shift, you're not going to have to mess around with the y values. Okay, just the x's.
Can you go back for a quick second?
Right, so when we're trying to find those 5 really important points, okay, to make our graph, to get them on a phase shift, keep the y's the same. Okay, all you have to do is go back to your original table, copy them down. If you're doing sine, copy the ones on the left. If you're doing cosine, it's the table on the right. All right, so if the y's are going to stay the same, it's the x's that change. All right, so to find your new x's, okay, look at what has been added or subtracted. Okay, does everybody have what's on the left? Right, so like in this problem, I'm going to look at what's been added or subtracted, and I'm going to do the opposite of that to all the x's in the original table. Okay, so what did I just circle here? What am I doing to x in this problem? Yeah, we're really shifting it right 90 degrees, or we're going to shift right pi over 2 radians. And we've done a minus pi over 2. So in order to shift it to the right, you're not going to minus pi over 2 from all your x's. You're going to do what? What would be the opposite? Add. Right? So you're going to add pi over 2 to all your x values, and that will shift them to the right. And that's just something you have to remember. Okay, phase shift, it's the opposite of what you would expect. Okay, does everyone have what's on the left side?
I'm just writing down the last bit.
All right, so the first thing I generally do when I have to graph is either if I have a reference sheet for the test, okay, look up what the original table is for sine, or probably you'll have it memorized since we're going to do it for probably 15 problems this week. Okay, we have a lot of problems with it. Okay. Right, so phase shift. John, we just said we're moving left and right. So which values are not affected? The y's. Okay, so I'm going to go back in my sine table, and I'm going to copy down my y's. Okay, somebody remind me, what are my y values for sine?
0, 1, 0, 1, 0.
Yep, 0, 1, 0, negative 1, 0. Okay, any question on that? Now, I'm going to write down my original x's, but I'm not going to put them in this table. Okay, I'm going to put my final answers in this table. So I'll put them off to the side. 0, pi over 2, pi, 3 pi over 2, 2 pi. And based on step 2, what am I going to do to all these x's?
Add pi over 2.
I'm going to add pi over 2. Perfect. All right, so plus pi over 2, plus pi over 2, just plus pi over 2 to all of them. All right, so when we do this, we won't be using decimals. Okay, we're just going to find a common denominator if we need to. Some already have it. And we'll just add them up. Okay, we're going to put our final answers right in that box. All right, first one, what's 0 plus pi over 2? Yeah, that's just pi over 2. How about pi over 2 plus pi over 2? Yep, 2 pi over 2. And if we can reduce it, we will. So what does that reduce to?
Pi.
Pi. Okay. The next one is pi over 1 plus pi over 2. Cameron, what would be my common denominator here?
2.
Yep. So to get a common denominator, double the top, double the bottom. What's 2 pi over 2 plus 1 pi over 2?
3 pi over
3 pi over 2. How about the next one?
2 pi.
Yep, it would be 4 pi over 2, or 2 pi. And now let's just go back and kind of look at the pattern we had.
So
1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2. How about this last one? 5 pi over 2. And if we were going to keep going, it would be 6 pi over 2, 7 pi over 2, 8 pi over 2, 9 pi over 2. It just keeps going up in the numerator by 1. We don't notice that once we reduce it, but that's how I'd like you to do it. Okay, always reduce it if you can. Okay, so any question on the table? All right, so the way I would grade something like this on the test, I'm going to give you 1 point for each x and y value you get right. All right, so right here, if you got this would be 10 points. Correct. Okay, and then the graph itself, that'll be worth 1 point. Okay, because the table is the harder part.
what do we do for the graph though?
Yeah, let's make our graph. All right, so my y-axis, I need to go up to 1 and down to negative 1. Okay, on the homework tonight, I already have graph paper for you. Does anybody want graph paper now? I have some. Nope. Okay. All right, and for our x-axis, well, I wouldn't go by ones on the x-axis. Okay, the reason is these numbers are awful to deal with. 3.14, 4.71, 6.28. We don't want to have to graph those. So what we do is we just scale our axes using these values. Okay? You can scale your axes any way you want, as long as you keep everything equally spaced. All right? All of these are equally spaced. Okay, we noticed a nice pattern to them. All right, that's 90, 180, 270, 360, 450. Right? So in degrees, that's what it would be. All right, so let's make this pi over 2, pi, 3 pi over 2, 2 pi, and that's my y-axis, that's 0. All right, now we just plot our points. Okay, so pi over 2, we're at 0. Pi, we're up at 1. 3 pi over 2, back to 0. 2 pi, let's see, negative 1. And 5 pi over 2, I need to label that. Back to 0. Right, now just connect those points. Remember that this graph is not sharp. Okay, the turns all should be nice, nice and smooth. And there's my graph. Right, so that's the new graph. Okay, if you want to just compare it to what the original would have looked like, it would have been 0, 1, 0, negative 1, back to 0. Okay, the one in blue, that's the original. Okay, so does that look like it shifted to the right? Good, yeah, that's what it should look like. Okay, so on the homework, instead of having you draw 2 on the same, I've got 2 separate grids, one for you to show me the original, and then one for you to show me the new graph. But that's all there really is to graphing a phase shift of sine. Okay. Any questions on that?
So how do we know like the original one? How would we just graph it? How do we know?
How do you know the points for it?
Yeah.
So the original, that's this table I gave you. Where is it?
Yeah. No.
Right here. This is the table we always start with.
Yeah.
Yep.
So how do you know the points? Because you said that, like for the new one, we just kind of make up the point for the x because you can't make the graph like pi divided by 2 and 3 pi over divided by 2.
Well, for the original, you're just going to graph those 5. That's always what you do.
Yeah.
Graph 0, 0.
Just in the first mark, so it's just.
Yep. Yep. Any other questions on that? All right, so that's a phase shift of sine. Let's try cosine. Okay, one thing I want to make sure everybody notices, when I've added or subtracted something to x, what do you notice in every problem that I have around the argument? I have it there, there, and there, parentheses. If you don't put in parentheses, it's not a phase shift. Okay? So if you see something like this, we're going to look at what this is next. That is not a phase shift. Now it's a phase shift. It's kind of a weird amount to shift by, 2 radians. You could, but without parentheses, it's not a phase shift. Okay, so make sure you don't make that mistake on the test. Okay? If it's a phase shift, you've got to have parentheses. All right, so Brendan, what's not going to change here? My x's or y's? Good. Do you remember what the y's are for cosine?
1, 0, negative 1, 0, 1.
Perfect. 1, 0, negative 1, 0, 1. All right, so if you get that right, you get 5 points just for the right y values. All right, now we're going to get our x's. Okay, the x's, okay, if you already noticed this, are the same for sine and cosine. They start out at the same spot. 0, pi over 2, pi, 3 pi over 2, 2 pi. Right, and Pat, what am I going to do to all these x values?
Bring a double each other or whatever it was. Right, because you got to get the common.
All right, we might need a common denominator when we do something to them, but what do we have to do that's going to make us have to do that? Has to do with this argument.
Multiply each of those by x plus 5. Right?
Does everyone agree with multiply? Subtract. Yeah, subtract. Okay, subtract pi from all those. Okay, some you won't need a common denominator for. Those three are pretty quick. But then pi over 2 minus pi. Shannon, what's my common denominator here?
2.
Yep, so 2. And Shannon, what's 1 pi over 2? Take away 2 pi over 2.
Negative pi over 2.
Yep, negative pi over 2. And my last one, 3 pi over 2. Take away 1. Same common denominator again. 3 pi over 2, take away 2 pi over 2. Yep, pi over 2. And if you wrote everything with a denominator of 2, you'd see a nice pattern here. That's negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, and we could keep going. 3 pi over 2, 4 pi over 2, 5 pi over 2. So, okay, any questions on the table? All right, now let's just make our graph. Okay, this time we do need to go into the negatives a little bit. Right, so we've got my axes there. So that's going to be 0, 0. And let's see, so we've got negative pi over 2. Okay, 0 I've already got labeled. Pi over 2 and pi. Okay, what's my highest and lowest y values? Okay, yep, negative 1's the lowest and page the highest.
What?
What's my highest and lowest y values?
1 and negative 1.
All right, so just label those. And now make your graph. All right, so we're at 1, 0, negative 1, 0, back to 1. Okay, it does kind of look like a V shape, but just remember that it's part of a wave, which would keep going. Okay, any question on that? All right, so there's our graph of cosine. Okay, so we did a shift by pi over 2 the first time. We did pi this time. We'll do one more shifting by pi over 4. Not because I really want to get the table, but I want you to see what happens when you graph it. Okay, something a little tricky we need to just be careful when we label our axes. All right, so it's going to be sine shifted by pi over 4. All right, so hopefully we're starting to learn some of those y values. So we'll just write those in quickly. And now my x values. Okay, Tommy Lee, what am I going to do to all my x's?
Subtract pi over 4.
Good. Okay, we're going to subtract pi over 4. Now, this is one, after we get a couple, you should start to see a pattern. And if we see that pattern, we'll just use the pattern. Okay, what's my common denominator for every problem I'm going to do here? 4. All right, so the first one, I don't think we need to do that one. No, just 0 minus pi over 4. Okay, next one. Yeah, go ahead.
Pi over 4.
Let's see. Yep, pi over 4. Okay, double the bottom, double the top. 2 pi over 4, take away 1 pi over 4 is pi over 4. Okay, anybody see the next one?
3 pi over 4.
Yep, 3 pi over 4. Keep going.
5 pi over 4.
5 pi over 4. And last one. 7 pi over 4. Now, let's just do one, just in case you're like, wait, where's this pattern coming from? Well, just do it out if you don't see the pattern. 3 pi over 2. Take away pi over 4. Double the bottom, double the top. That's 6 pi over 4. Take away 1 pi over 4. 6 take away 1, there's your 5. Okay, so if you don't see the pattern, you can always do out the common denominator each time. All right, so now our graph. Okay, is there a 0 in the x column anywhere this time? No. All right, so that's something we need to be careful when we set up our axes. All right, so let's put negative pi over 4. Okay, I'm not going to label anything here. The y-axis, that's 0. I'm going to put pi over 4 right there. Where does 3 pi over 4 go? Would it go right here? No. In between them?
Yeah.
That's remember, this one is 0.
Well, not exactly, because it would be somewhere between.
Nope, 3 pi over 4 is bigger than pi over 4, so it is going to be to the right of it.
But the third line.
This is 45, this is 135, if you want to think of it in degrees. So where would 3 pi over 4 go?
Getting the third line.
On the third line, right. Okay, you have to keep your spacing consistent. So if that's the width of my space between my labels, I have to keep that width all the way through the problem. Okay? So in this case, we end up skipping every other label. Okay, and I think I'm going to need one more for 7 pi over 4. Hey, any question on that spacing? Okay, and it's all because we didn't go through 0. That's why. If you don't space it right, what you might get is a graph that looks like this. It looks really like squished in one part, but then stretched in the other. It's because you didn't space things correctly. And now we'll just graph our points. 0, 1, 0, negative 1, back to 0. All right, so any questions on phase shift? Okay, I think that's the harder one we have to do today, because when you're doing a phase shift, you've got to deal with pi. You've got to find all these common denominators. It'd be a lot easier if we could just keep the x's the same and we didn't have to mess with them. And all we had to do was add or subtract something to the y's. Okay? Because the numbers here are just zeros, ones, and negative ones. Okay, well, that's our last transformation for today. Okay, vertical shift. Okay, so vertical shift is going to move your graph up or down. Okay, and it has the form y equals sine or cosine of x plus or minus d. Okay, and I would advise you in your notes, use the letters I'm using, because this is going to tell you when you have all the transformations in the same problem, the order to do them in. So there's 4 transformations. This would always be the last one.
They're supposed to be in parentheses now.
No parentheses here. Okay, so this time what you're adding or subtracting is outside the argument. If I put parentheses around the x and the d, what would that make it?
Phase shift.
That'd make it a phase shift. Okay, so this time no parentheses around the x and the d. And generally d is a nice number. So we may shift it up by 1 unit, 2 units, 5 units. Okay. We usually use whole numbers. And what you would expect to happen is what happens. Add is going to move it up. Subtract is going to move it down. Right, did we play the phase shift? Did we do the sound frequency for that? No? Remind me at the end. We'll play a phase shift. I'll show you what that sounds like. For a vertical shift, there really is no connection with sound. Okay. Every other transformation we do, whether it's a phase shift, a vertical stretch, or horizontal stretch, they all have something to do with how you would hear it. But not a vertical shift. Right, so last thing before we can make our graph, just figure out what stays the same, what's going to change. Right, so Adriana, if we're going to shift up and down, what doesn't get affected, the x's or the y's? Yeah, the x's. Okay, which is great because this time we don't have to deal with all the pi's. Okay, just keep them all the same. Okay, so we're going to change the y values. And this time all you have to do is add or subtract whatever d is to the original y values. Do not do the opposite. Okay, plus will shift up, minus will shift down. Okay, all the vertical transformations, you do exactly what you would think you would do. All the horizontal ones are opposite. And that's it. That's all we have to do for a vertical shift. All right, so Fernando, looking at this one, is that a vertical shift or a phase shift?
Vertical.
Yep. How do you know it's a vertical and not a phase shift?
Because there's no parentheses.
Perfect. There's no parentheses around the x and the 2. What if I did that? Is that a vertical shift or a phase shift now? That's still vertical. It's got to be between the 2, right? Phase shift, it's got to have the x and the 2. And that doesn't. All right, so Tyler, since we're doing a vertical shift, what values stay the same again?
Exit.
The x's. Okay, we're going to shift up and down. We're not going to do anything left and right. So go to your table and copy those down. So 0, pi over 2, pi, 3 pi over 2, 2 pi. And Jill, what are my y values for cosine?
1, 0, -1, 0, 1.
Perfect. Okay, I'm just going to write them off to the side because those are not my final answers. I'm going to put my final answers in this table. Okay, and Will, what am I going to do to all those y values?
Subtract 2.
Add 2. Add 2. This one, you just add or subtract whatever the number is. Don't do the opposite for this one. But that's a mistake a lot of people end up making. Okay, don't do the opposite. All right, so add 2. All right, so Eric, what would I get if I add 2 to all those?
You add 2 to all the 1, 0, negative.
Yep.
So you get 3, 2, 1, 2, 3.
Perfect. Okay, so my highest y value is 3. Lowest y value in this case is 1. So this is my x-axis, y-axis. Now, when I label my x's, anytime I do a vertical shift and just a vertical shift, you're always just going to label them using the originals. It's always 0, pi over 2 pi, 3 pi over 2, 2 pi. All right, so up at 3, down to 2, 1, 2, back to 3. You just try to make it look as smooth of a curve as you can. That's fine. All right, so any question on shifting cosine up to? All right, so why don't you guys try that one? See if you can take sine, shift it down 3. Then we'll finish it up together, and then we'll play a phase shift. Okay, we'll see what that sounds like on the speaker. All right, so our last one. Okay, we know this is a vertical shift because we do not have parentheses around the x and the 3, or negative 3. All right, so Derek, what column stays the same here?
X.
Yep, x's. And Dalton, can you remind me, what are my original x's?
0, pi over 2, pi 3 pi over 2, and
2 pi. All right, so you got our original x's. Original y values, I'm just going to write them down for reference, but remember they're not the final answers. Brian, what are my original y's?
0, 1, 0, 8, 1, 0.
Yep. And now it's a simple calculation. We just have to make sure we do it the right way. Do we add 3 or subtract 3? Subtract 3. Okay, we're going to subtract 3. All right. So how about Tyler? Can you tell me what you get if you minus 3 from all those?
Negative 3.
Yeah.
Negative 2.
Good.
Negative 1. I mean, negative 3.
Negative 3. Yeah.
Negative 4. Negative 3.
And negative 3. Okay, so again, 1 point for each x and y value you get correct. And then 1 point for the graph. All right, so let's label it. We need to go down to negative 4. So 0. And make sure we label our x's. Okay, if you don't label your x-axis, what do you think I'm going to assume you're going by? What do you think? Karen? Anytime you don't label an axis, what do you usually go by?
We usually go by sorry, what was the question?
Like think like back to like graphing, like 4th, 5th grade kind of stuff. If you don't label these lines, what do they always assume you're going to go by? Ones. Yeah, you always go by ones. So if you're not labeling these, I'm going to assume you mean 1, 2, 3, 4, 5. Okay, if that's not what you mean, then put in the labels pi over 2, pi, and so on. All right, let's see where we're at. So 0, negative 3. Pi over 2 is negative 2. Pi back to negative 3. Negative 4 and negative 3. Right, so there's our graph of sine shifted down 3. Okay, any question on that? All right, so as I said, this one, no real connection with sound, but a phase shift, there is. Okay, so let me, let's just get these at the same volume, same frequency, same phase. All right, so I'm just going to play this frequency. It's about a little over 1,000 hertz. Turn it up a little. Okay, we might say that's a pretty, it sounds like a high-pitched sound, but we can actually hear up to around 20,000 hertz, or maybe 19,000 if you're young enough. 20,000 would be hard to hear still. But tomorrow we'll see how high and low people can hear. But for now, I'm just going to stick with that frequency. Okay. What I'm going to do is start to change the phase. Okay. Anybody have a guess what that's going to sound like as I change the phase? High pitch, all right, so that's one thing that could change. You could change the pitch of a sound from low to high. What else can you change about a sound besides its pitch? What do you mean by tone? Well, if I had different instruments, I could change sometimes they call it the timbre, the way it sounds. Like if you play a certain note on a piano, it's going to sound different than the same exact note on a guitar because they're different instruments, and even though it's the same mathematical frequency, they sound different because of the type of instrument. But I can't really change the characteristics of the sound. I can just generate beeps. That's all I can do. So it's still going to sound something like a beep. But what else could I change besides the pitch of that beep?
How long it is?
That's just controlled by the start and the stop. So that's me, how long I leave start on.
Frequency.
Frequency is the pitch.
Okay, can't change anything.
There's one more thing you can change, like pretty common thing. What else can I change about a sound?
Volume.
Volume, there you go. I can change the volume, all right? So,
Volume's on the bottom, you didn't change that, that's why.
right. So, in terms of a phase shift, okay, the way we hear it, it's either going to be a change in the pitch or it's going to be a change in the volume. Those are the only two things that can change. All right, so let's put it back and play it. So what happened? It started to get quiet, and then if I keep going,
It got higher.
it'll start to get louder again. So if you could get it just right, that's not perfect, but if I could get it just right, you wouldn't hear, or you'd hear very, very little sound. The way this would work best is if you could set up 2 speakers outside, okay, in a place that doesn't echo, and as you change the phase or you walk between the speakers, all of a sudden it would sound louder in one spot, and then if you walk back towards the other speaker, it would sound softer. That's the effect you'd get. Again, I can't really do that effect in here because of the walls and it echoes. But that's how we hear a phase change. Okay? Not because I changed the volume. Okay? Volume stayed exactly where it was, just because we changed the phase. Right? So any questions on that? Right, so that's what a phase shift sounds like. Tomorrow we'll look at frequency change and then an amplitude change, okay, which is stretching and compressing vertical and stretching and compressing horizontal. Okay, so we'll play some of those sounds and see what they sound like. All right, so the homework tonight is these 7 graphs. Okay, I'm going to pass out a worksheet. These graphs are already written down on the worksheet for you.